Okay, welcome back. This is the second lecture for Monday, March 30th. So for homework, what we're going to do today, this homework is going to cover what we do. I want you to do 8.8 and 8.14. Again, this is due Wednesday. Please make sure you turn in the homework because, again, you cannot pass the class if you don't have a 70 average on the homework. The drop date is actually extended, I believe, until either May 14th or the 17th. I'm not sure, but they've extended the drop date. So you can go all the way up to the very end and drop the class should you so desire. And that's okay. But again, I've only received about 10 to 15 emails with this last homework on it. And I do expect you to turn it in. I assume that you've been keeping up with all the broadcasts by both the university administration that the course shall be stayed. In other words, we shall complete the class as usual, except I'll have to do it in a different manner, which I can do. Anyway, homework 8.8, 8.14. Please turn it in with the find VO across the 6 ohm resistor on the sample test problem 5. So what we're going to do is we're going to cover AC circuits, and this is pretty straightforward stuff. There are a couple of issues that you have to keep up with, so I'll kind of go over those. But for right now, what we're going to do is we're going to look at keeping everything into ohms, how to get resistors, which are already in ohms, and capacitors and inductors, which are not in ohms. We're going to figure out how to turn those into ohms and reduce a circuit. So here we go. So far, we've been looking at time domain, both DC and AC circuits. In the DC part, we had the voltage was either on or off. You could get a step function, kind of like the last lab that y'all did, where you had the step function that went up and then turned off. So DC voltage is either on or off. Now, AC voltages and current can be based on a cosine function or a sine function. We're just going to say that everything we deal with in this class is going to be a cosine function. That way we have no ambiguity of is it a sine or is it a cosine. We're just going to assume everything is cosine. And basically, the time domain value was a peak value, V peak or V max. I think the book calls it V max. Cosine omega t plus or minus theta V. And the current equation in the time domain was I peak cosine omega t plus or minus theta I, where omega is 2 pi f and f is the frequency. Also, so far what we've looked at is we've looked at capacitors and their value is farads. We've also looked at inductors and their value was henries. And we've looked at resistors and their values were always in ohms. So everything we've done in the time domain, we've come up with a differential equation. And I don't know about you guys and girls, ladies, gentlemen, all, I guess I should say, or maybe it's everyone nowadays, being the politically incorrect person that I am. Anyway, I don't know about y'all, but I don't like differential equations. Number one, you can only solve 10% of them, and the other 90%, some of them you can't never solve. So anyway, what's great about the AC is I can go from the time domain, I can change AC into a frequency domain, and that makes everything nice and easy now. And basically the frequency domain, how to do that is, it's called a phasor format. It's a frequency domain and everything comes into a phasor diagram, which is basically a magnitude and a phase angle. Complex number. Or you could also have it as a real and a reactive part. So it depends on how you look at it. I don't really care how you answer problems. I mean, all I do is hit a button on my calculator and get the answer that you came up with. So it doesn't matter to me how you do it, but we're talking about phasor frequency domain, phasor domain, some people call it phasor domain, and you can go back and forth with that. They're kind of synonymous, but not necessarily. So anyway, if you take a V equation, a voltage time domain voltage equation, and so it is V of t equals V max or V peak cosine omega t plus or minus theta V. And I can go from that time domain, I can go to the frequency domain. And this is going to be a phasor that is V max at an angle of whatever theta V might be, plus or minus whatever that angle is, which I can then change into a rectangular format instead of a polar format. This is the polar format. All right. I can do that also with a current equation. If I have a current equation, it can be I t cosine omega t plus or minus theta I. Then I can turn that into I max at an angle of theta I, whatever that plus or minus angle might be. Remember that 2 pi f is omega and f is the frequency. So the big thing with this, when you're doing this, seems to be pretty easy to change the time domain voltage and the time domain current into a phasor. But what you have to do now, since you're going into the frequency domain, you have to figure out what are you going to do with the capacitor and what are you going to do with the inductor. So many, many moons ago, a long time ago, they decided that they were going to use complex numbers. Since the phasor domain of the voltage and the current is a complex number, we're going to take the impedance, which is the real and the imaginary value of a circuit, and we're going to turn everything into ohms. And the way you do that is you take XC and, depending on how you look at it, minus J, or J is in the bottom, 1 over J times 2 pi f omega times C, or bring the J up top and it becomes minus J times 1 over 2 pi f times C, and I get a value of ohms out of that. The same with the inductor. I can change the inductor into an ohm value by multiplying times J by J times omega times L, or 2 pi f times L, and I get an ohm value. Okay? Resistors will always stay in ohms. Not a big deal. So in the RMS frequency domain, now this is a different domain. One of the problems is that back in the 20s, early teens, 1900s, early 1900s, everybody was very familiar with DC. And so they wanted to make AC like DC was. And so one of the things they came up with is, hey, if it's power across a resistor in DC and that power across that resistor is 40 watts, then we want AC power across that resistor to also be 40 watts. Well, that presented a problem. So what they decided to do was they decided to go to RMS, or root mean square frequency domain. And basically how you do that is go from the regular frequency domain that I talked about a minute ago, we're going to go to the RMS frequency domain and make everything easier. In other words, every time you see a non-sinusoidal function on a homework problem or a test or something like that, you're going to assume that it's already been changed into an RMS value. And this is how you would do it. You take the Vmax value, divide it by the square root of 2, and the angle stays the same. The same thing happens for an IRMS value. You take Imax, the peak value of the current, time domain equation, divide it by the square root of 2, and you have an angle theta I on it. So we're going to, like I say, we're going to assume that everything from now on is always going to be RMS, and it's also always going to be divided by the square root of 2 before we begin doing anything. This makes it easier on everybody. Maybe it messes with your head. I know some students have a hard time with this, but if you remember, it's already an RMS value. I don't have to deal with the square root of 2, and when we get to the power, I don't have to deal with multiplying it by or dividing it by 2, the real power or the imaginary power. But again, today we're just dealing with impedance. Okay, once again, omega is 2 pi f. F is the frequency. We're changing all the inductors, capacitors, and the resistors are already in ohms, but we're changing the inductors and capacitors into imaginary values. Once you do that, then everything you've learned in DC works for AC. Ohm's law, same stuff. KVL, KCL, all the same stuff. There's no difference. KVL, voltage divider. Sorry, I messed up and I didn't want to do it over. I'm lazy, too bad. Current divider, you have mesh, you have loop, you have Thevenin. It's all the same. Superposition, source transformation, which we really didn't go over too much. We kind of touched on it, but not a lot. And then in DC, here's the major difference. In DC, you had real power only. In AC, you have different powers. So you could, and we're not going in there today. We're going to go there later. But that's the major difference. You're going to have different powers in AC than you did with DC. Okay.